Good afternoon, everyone. Welcome to this mini school on quantum simulation, which is going to be done by the Ian Joe David, who is a PhD student at the University of KwaZulu-Natal under the my and Francesco Petruccioni supervision. And his PhD is related exactly to the things which he is going to talk about, but during this mini school, he will describe it in a little bit easier manner. Okay, Ian, take it over.
Okay, good afternoon to everyone who's attending in person and also in Zoom. So as Ilya just mentioned, I'm going to be giving a mini school for the next month on the quantum simulation of closed and open quantum systems. So as Ilya mentioned as well, this is what I do for my PhD. It's my research. I've been doing it for a very long time. And I really wanted to present this mini school so that I could not only just educate others at my research group and in the NITheCS, anyone associated in NITheCS, but I also wanted to garner some interest around this field as it is a very important application of quantum computing. And as you will hear throughout the first lecture of this course. So let me just show you the outline for the mini school. So you would have seen already in the advert what we're going to be doing for 5 lectures. So I'm very fortunate that July has 5 Wednesdays. So I will be able to actually spend the first lecture giving you a sort of nice overview, motivation to quantum simulation, and also talk about some preliminaries for those that don't necessarily work in quantum computing, quantum physics, just so that we're all on the same page, and I can fix some of the notations of things that I would use throughout the school. So that's what we'll do in the first lecture, and then we'll spend the rest of the lectures discussing methods. So really what I want to do is in the first lecture just build up to understanding the problem of quantum simulation. And once we understand what the problem is, then we're going to spend the next 4 weeks just talking about the different methods to solve the problem of quantum simulation. So we'll spend like the second lecture talking about the famous Trotter's product formulas for closed system simulation. We'll spend the third lecture talking a bit about some more modern and novel methods for simulating Hamiltonians. And then we'll spend the last 2 lectures discussing the quantum simulation of open quantum systems, which is a bit more tricky than doing closed system simulation. So we'll go into a bit of the intricacies of simulating open quantum systems, discuss some examples of simulating something like a single qubit open quantum system, and maybe talk about also the modern techniques that are developed for simulating open quantum systems. So, to not waste any time, let's jump straight into the first lecture. So we're all here. I think the most important question, and maybe if you don't know what this is you're going to ask is, what is quantum simulation? Okay, so quantum simulation involves using a controllable quantum system to study the behavior of another quantum system that is difficult to study directly. Okay, so this idea of using a quantum system to understand the behavior of another quantum system was proposed by Richard Feynman and Yuri Manin independently in the 80s. And they proposed this idea of using one quantum system to simulate another quantum system or to understand the behavior. So that is all quantum simulation is that we have some controllable quantum system and we want to use it to understand the dynamics of another quantum system, something that we can't study directly. And we'll talk more in detail about why this is important. So this is Richard Feynman here. We all know the famous paper by Richard Feynman on simulating physics with computers. And in this famous paper, he proposed basically the idea of quantum computing. So the idea of quantum computing was actually inspired by the need to simulate quantum systems and physical systems. And when they proposed this idea of using a quantum simulator, this inspired the idea and the development of quantum computing. Yuri Manin, a Russian mathematician and physicist, also proposed the idea, and you'll actually notice, I think, his paper on computable and non-computable was actually 2 years before Feynman. I think only recently a lot of people have been citing Yuri Manin, but it's very interesting to see that somebody did it 2 years before Richard Feynman. And in fact, I think if you go onto the Wikipedia page, they actually credit the inspiration for the development of quantum computing now to Yuri Manin. So that's just a little bit of history and where this comes from and why this is such an important problem to think about. It's because, firstly, we talk about quantum computing. There's been mini schools previously on quantum computing. I've given one of them, in fact. And you wonder where this came from. And this is the inspiration, the need to simulate physical systems. So as I mentioned, this idea of using a quantum system to simulate another one inspired the development of quantum computing. And there's so much out there about why quantum computing is important and why it's going to change the world and change the future. So I won't talk about that, but at least the history of knowing why this was developed was to solve particularly this need of quantum simulation. So now that we understand basically what quantum simulation is, let's go into a bit more detail. Now, let's talk about why we need quantum simulation. You may ask, okay, we already have computers. Why don't we just use regular computers to simulate, quantum systems? Well, unlike classical simulations, quantum simulations, they leverage the quantum phenomena, such as the state space of qubits or entanglement and other things like superposition, to do sort of simulations of quantum systems that provide some advantage over classical computers. And the biggest advantage that I can give you is the fact that classical computers will struggle with simulating quantum systems because of the exponential growth of the Hilbert space. If you know anything about quantum mechanics, you know that if you want to talk about, and we'll talk a bit more in detail about it later on when we look at the example of spins. But for now, just as an overview, you know that the Hilbert space is very, very large. And to try and realize that on a classical computer will require a lot of memory, a lot of storage. And this means that you don't have any sort of advantage in simulating very large quantum systems, like we find in many body physics and quantum chemistry. And we also need quantum simulations because, as I said, it can provide some insight into things like many body physics, quantum chemistry, and even material science. If we can have simulations of quantum systems that provide us an advantage over the current classical computers that we have, then it means that we can better study systems like condensed matter systems, or even develop better materials, and even study things like quantum chemistry. So I should mention that I've only discussed quantum simulation so far. It is a broad field, and it comprises of two different types of quantum simulation. So you get something called analog quantum simulation and digital quantum simulation. Analog quantum simulation directly mimics a target quantum system using a physically similar system that can be controlled. And this is done, and you can also read about something called analog quantum computing. So the way we do this analog quantum simulation is it's done through analog quantum computing, which applies continuous transformations to continuous quantum states. So if you're interested in analog quantum computing, you can go Google it and read about it. But the main idea of analog quantum simulation is that you have some physical quantum system that's controllable, and you're able to control the system in such and transform the system in such a manner that it mimics the dynamics of some target quantum system that you want to simulate. So an example that I provided a reference to the paper here is this fermionic atoms hopping in an optical lattice being used to simulate quantum chemistry. So they have some molecule that they want to simulate, and they effectively make a mapping from this to the Hamiltonian that describes this fermionic atoms hopping on the optical lattice. And what they will do is, by controlling this system, they can effectively mimic the dynamics of the molecule that they are trying to study. So you can read about this in Pierre's Quantum if you're interested. So for this school, we're not going to be talking about analog quantum simulation. We're going to be talking about digital quantum simulation. And digital quantum simulation, it basically just uses a quantum computer to simulate the dynamics of a quantum system by breaking down the simulation, or by breaking down the unitary evolution of your system into a sequence of quantum gates that can be run on a quantum computer. And the reason why this is called digital is because as I say here, it relies on digital quantum computing, which means that the computation is broken down into discrete steps. And you're not using continuous states, you're using qubits instead of using continuous variable states. So an example of this will be to use a quantum computer and a method such as Schrotter-Suzuki product formulas to simulate Heisenberg spin chains. So what you would do is you'll start off with your physical system, which is just spins on some sort of ring or even just open on a chain. You will then start by coming up with a Todd-Suzuki product formula, which will approximate the unitary evolution of that system. And then you'll realize that product formula by some quantum circuit, which you'll run in quantum computer. And that is how we'll do this. We do the simulation quantum system digitally. That's just basically just what digital quantum simulation is. We're going to be focusing on this for the rest of the mini-school. So all the methods that we'll talk about and analysis will be related to digital quantum simulation. So the other important question, which you've probably seen from the title of the mini-school, is what types of quantum systems do we want to simulate? The first is a closed quantum system. And this is a system that is isolated from the environment. So see the picture that I have here, you have the system, the environment, and it's not allowed to interact or exchange information or energy or anything like that. The system is completely isolated from its environment. And the system evolves and its dynamics are described by the Schrodinger equation. So that is a closed quantum system. We're going to spend the first few lectures talking about how to simulate the dynamics of this type of system, the closed quantum system. The second type of system we want to simulate is an open quantum system. This is a system where the system is allowed to interact with its external environment. Okay, it can exchange energy, information, and matter. And the system evolves according to the Lindblad-Master equation. And this master equation incorporates things like dissipation and decoherence. We'll spend the last 2 lectures of the school talking about simulating this type of evolution. So you obviously hear from different fields and different backgrounds, and you might be asking yourself, okay, so what are the applications of this quantum simulation that I'm talking about? Well, depending on where you come from, some of these applications may interest you. So for example, if you're just studying fundamental physics, you're interested in things like high temperature superconductivity. See this little figure that I took from Wikipedia, and it's just a phase diagram for a high temperature superconductor based on iron. These experiments that people do to understand high temperature superconductivity, doing things in the lab and even doing numerical simulations are costly for classical computers. But there's been a lot of work recently that's gone into applying methods for simulating Hamiltonian dynamics to understanding dynamical phase transitions. And as the quantum hardware develops throughout the NITheCS era, we hope that it'll one day be possible to use the methods from quantum simulation to better understand dynamical quantum phase transitions and maybe better understand high temperature superconductivity. So this next picture is just a standard quantum phase transition diagram, talking about the different phases ordered in quantum disordered. And we hope as well that we can use methods from quantum simulation to better understand these processes that occur in fundamental physics. Because quantum simulation solves a very fundamental problem, understanding the dynamics of a quantum system, given the equation or its equation of motion. So using quantum simulation, we should be able to understand these types of phenomena, such as high temperature superconductivity and phase transitions, and give us more insight into these topics that we probably can't achieve with classical computers. Another sort of application will be quantum chemistry. So if you've done any sort of quantum chemistry, you may know that that molecules are very, very hard to simulate. They're not easy to simulate, even numerically. And we can obviously write down these types of Hamiltonians that describe the molecule, and then we can simulate them efficiently using quantum simulation, which will give us a better understanding of ground state energies of these systems in quantum chemistry. We can also understand the dynamics of protein folding problem, and you can even use quantum simulation for things like drug design and materials. So I won't go into any of these applications in detail, but these are things that you can look into, and there are many papers online that you can find that talk about this. And lastly, the application I want to talk about is high energy physics. So recently, there's been a lot of work into looking at simulating on a quantum computer quantum field theories. And the reason why you'd be interested in this is because if you look at any quantum field that you have, it's infinite over all space. And usually when they do simulations like in lattice H3, they make truncations and stuff, but these lattices are still extremely large, and simulating on classical computers is quite tough. But doing it on a quantum computer, of course, you have the advantage of the state space of qubits, which means that quantum simulation will provide you an advantage in simulating things like lattice H3s and even particle interactions. as a lot of modern research is going into trying to understand how to use quantum computers to simulate sort of phenomena in high energy physics, with even novel quantum algorithms being developed to simulate path integrals on quantum computers. So now I'm going to state a very informal version of the quantum simulation problem. Once I've done that, I'm going to walk you through all of the preliminary information that you'll need to understand everything that's going on in here. And then once we have the preliminary understanding, we're going to formalize this problem, formally state the problem so that we have an understanding of what we're going to be solving over the next coming minutes. Okay? So what is the problem of quantum simulation? Let's look at just very, very colloquially the state space of a quantum system. Then quantum states are usually described by state vectors, unit vectors in this Hilbert space. And the dynamics is governed by the Schrodinger equation. And so a state that's at some time t equals 0 will evolve in time, and it will reach a state at some time t. The quantum simulation problem is very, very simply, all we want to do is realize this dynamics, the dynamics that you see here, on some quantum computer. So such that the output of our quantum computer, or the circuit that we run on our quantum computer, gives us a quantum state that is within some precision epsilon close to the true state. We just want to use the quantum computer to realize these dynamics in such a way that we have an approximation to the final output. And I will make these definitions a bit more formal as we go on. But effectively, how it works is that we know what our initial state is. We prepare that state on a quantum computer. We approximate the dynamics of this unitary evolution using a quantum circuit. And whatever the circuit outputs is going to be epsilon close to this, the final state at some time t. So this is just an informal statement of the problem. Let's talk about the preliminaries that we will need to solve, to state and then solve this problem. So, as I've mentioned in the advert, this school is for anybody who's interested in quantum computing, quantum physics, or just has an interest in this problem. So I want to take just a few minutes to just talk about some of the background information you may need. So when I mention these things going forward, you will at least have some idea of what I'm talking about. Of course, this is by no means some rigorous explanation of all four of these preliminaries. If you want that, Google is your friend. You'll be able to find everything you need there. So let's talk first about the mathematical preliminaries you'll need to just start understanding the concept and even the problem of quantum simulation. So you'll need to understand things like Hilbert spaces, operators and matrices, norms and metrics. You'll also need a little bit of understanding of big O notation, and then how to approximate functions. So let's talk about this in a bit more detail. So of course, a Hilbert space is just a complete complex vector space with an inner product definable space. If you don't know what that is, you can Google what a Hilbert space is, and it'll give you a little more understanding of it. But this is just a standard definition from any quantum mechanics textbook that you can find. But for at least the purposes of whatever we'll be dealing with, we'll just consider that our Hilbert space is just a vector space of complex numbers, or just D Cartesian product of the complex numbers. So just a D-dimensional complex vector space. That's most of what we'll be dealing with. And of course, a state or a vector inside this Hilbert space is just going to be a D-entry column vector where each of these complex numbers. And of course, the inner product that we'll use will just be the standard inner product of a complex vector space, where if you have two vectors that are in the space, then this is how we define the inner product. That's the inner product on the Hilbert space. So that's all I want to talk about Hilbert spaces. And then we just talk about what an operator is. An operator on the Hilbert space H is just a linear transformation from H to H. And what does it mean? Linear transformation, if you have some linear combination of vectors from H, then applying operator A on this linear combination just allows you to distribute the operator in past the constant and even across the sum. That's all it means to be linear, right? And we also know from standard linear algebra course that you can always represent operators by matrices. So if the operator acts in a d-dimensional Hilbert space, then you can represent it by d matrix. That's all I want to talk about with that. And then something else that we'll use throughout the course will be functions of operators. Of course, we'll see later on when we talk about the evolution of the quantum system, we'll need the exponential function of some type of matrix, which would be a Hermitian matrix. But effectively, given some function f and an operator, we can define the function of A using just the Taylor series. So if you might remember the Taylor series from your first year maths course or calculus course, but effectively you just have f of A is equal to this infinite sum. We have the nth derivative of f evaluated at some point x naught, and you just have the operator A minus x naught identity to the power n. This is standard Taylor series, and we'll use this to define the function of an operator. So something that's very important to us will be the exponential function of an operator. This is like, the main thing we're going to be dealing with for most of this course. So I just give you how we define the exponential function of an operator here. And this is for x naught is 0. We'll always use x naught is 0. It just makes our analysis easy. So that's how we define the function of an operator. It's fairly straightforward. The next important mathematical concept that we'll need for the school will be norms and metrics. Okay, so a norm on a Hilbert space is just a function that allows you to sort of measure the length of a vector. I use inverted quotes because, of course, length is just a sort of analogy to how we measure the length of a vector from the origin to some point in a Cartesian plane. But it's basically just defined using the inner product that we already have, right? So we can always talk about the norm using the inner product. So we can say that the norm of some vector in a Hilbert space H, but sometimes to make it easy, we just write it in terms of without the kept vector on the inside. Is just the square root of the inner product of the vector. It's fairly straightforward. And the norm has the following properties. Of course, the norm is always positive real number of 0. It satisfies a triangle inequality. This triangle inequality of norms is going to be extremely important in doing our analysis of the error that we get when we do quantum simulation. And it also satisfies this property here that for any complex scalar C times your vector, the norm of the whole thing is just the absolute value of C times the norm of that. These are just 3 important properties of the norm that you should keep in mind as we go through this mini-school. Okay, and you can have basically any type of vector norm, and as long as it satisfies those properties and the definition of a norm, you can have different types of norms. I'll just talk about some common norms that you might see throughout the school. The P norm or the LP norm is just defined that if you have some vector in a Hilbert space, a d-dimensional vector, then the P norm of this vector is just the sum over I from 1 to d, xi absolute value up to the p should be on the outside of this absolute value, and it's all raised to the power 1 of p. Okay, and for p equals 2, we of course get the standard Euclidean norm. So this is just the p norm. The other important norm that you might see will be this infinity norm, and this infinity norm is just the maximum of the absolute values of all of the entries in the vector. That would be the infinity norm. You can obtain the infinity norm from the P norm by just taking P going to infinity. Okay. We can also define norms on operators, and this is going to be very important for us because we are going to be comparing, the norm of the difference between operators when we do quantum simulation. So we need a way to understand, or we need a norm on the operator. So I'll define the norm of an operator, and then I will explain. So the concept of like length of a vector is just an analogy we use when we talk about vector spaces. And it may not seem clear how this relates to operators on, just at a first glance. But because the space of operators is also a vector space, you can also have a norm on this space. So let's talk about the definition of the operator norm. So for some operator A, which maps from the Hilbert space H to H, the operator norm is defined as the supremum of the ratio between the norm of the operator on some vector psi divided by the norm of psi. And this is for all vector psi in your Hilbert space, right? Already you start to see some problem that it's hard to sometimes calculate this norm directly. But to give you some understanding of what this norm actually tells us, it's just the ratio between some vector psi and how much A transforms psi. So if you have to think of psi as being vectors in the Cartesian plane and A being some linear transformation that probably just stretches the vector, right, that scales the vector, then this norm, this operator norm, will just be the ratio between how much A scales psi to psi. And it'll be the supremum, so the least upper bound of the set over all the vectors in your Hilbert space. So you can see that, whereas we can compute vector norms directly, like for example the Euclidean norm, computing the operator norm is a lot more tricky, because now if H is just a d-dimensional complex vector space, you need to actually find, for every psi in that vector space, that's an infinite dimension, that's like the infinite psi set, right? There's infinitely many vectors in that set. So solving these operator norms and finding these operator norms is in itself a very important problem in quantum simulation and quantum computing, and even classical computing, because usually this requires some important techniques from something like probability theory and ensemble theory to kind of estimate an average of this quantity, or even solving sort of optimization problems to figure out what will be this operator norm. Fortunately for us, because of those properties of the norm that I just mentioned, we can use this norm and obtain bounds by using things like triangle inequality, Euler's inequality, and any other type of relation without directly solving the operator norm. And that's effectively a very, very nice way to understand things like error and even distances without actually computing this very, very complicated quantity. And another important inequality that we will use throughout the mini-school will be this inequality, which relates just the norm of A on some vector psi. It says that it's bounded about by the operator norm of A on some vector psi, or the norm of the vector psi. And we'll talk later about why that's. Okay, so we spoke about how you can calculate the norm for an operator, but we can also define a norm on matrices, right? Because of course we can represent every operator in a matrix. So a very important norm that you'll use for matrices in this course will be the trace norm. So if you have a D by D matrix A, then the trace norm is just given by the trace of the square root of A dagger on A. And where this A dagger represents just the complex conjugation transpose of the matrix A. So this is the trace norm, and it's used quite a lot in quantum information theory and quantum computing. And we'll also use it in this course as well when we talk about simulating open quantum systems. Okay, so we can use, so far I've only spoken about what a norm is. However, when you do quantum simulation, you also need this idea of distance. And whereas a norm only measures sort of like a length, what we need is just a metric or a distance measure that's on the Hilbert space, so that we can actually determine what is the distance between our true state and the final output state that our quantum computer gives us. So using the norms that we've already defined, we can just go ahead and define a metric. So if you don't know what a metric is, it's just a function that accepts two inputs from your space, and it maps it to a real number. So it gives you some sort of idea of a distance between these two entries in your space. And the metric satisfies a bunch of properties, like it should always be a positive or zero real number. If both arguments are the same, it should be zero, it should be symmetric, it should satisfy triangle inequality. You can just find those properties online. But we can use the norm to define what the metric is. And for example, if I want to use the P norm, for example, I can define a metric on the space of vectors, which we call a P metric, between two vectors psi and phi, as just the difference between psi and phi, and then you evaluate the P norm. So that's one way we can define a metric on the vector space. And we can do the same for matrices as well. So we can use then the trace norm to define a metric for the matrices. And you'll notice that where in the previous example, I just used the norm to define the metric explicitly, here I have a factor of a half. So this is just a quantum information science convention. And the reason, which we'll find out later on, is that usually when A and B are represented by quantum states, or density matrices, putting this factor of half there guarantees that the metric is always bounded about by 1. So that's why you'll see half in the literature, or even when you Google. If you may be curious why you need a half, because even if you just use the trace norm, it will satisfy all the properties of the metric. But the half is just there to make sure that it's upper bounded by 1 whenever A and B are quantum states. But in this case, A and B are just matrices, they're not density matrices or anything like that. Okay, the third mathematical preliminary we'll need, which maybe if you're a physics student, or if you've done computer science or mathematics, maybe you didn't see this before, but this is very prominent in the field of quantum information science and computer science. It's the idea of the big O notation and the asymptotic notation. So if you haven't seen this before, all it is a mathematical notation that will describe the limiting behavior of a function when the argument tends towards some particular value. So where you see this is when you talk about algorithm theory and run transfer algorithms, or even approximation theory when you talk about error. You want to understand, as the argument tends to some value, how is the function itself behaving? And we'll just formally state it, and I'll give you some examples, right? So if you consider some real or complex value function f, and you let g of x be a strictly positive comparison function, then we usually say that f of x is a big O g of x, which you read it like that, as x tends to infinity. And what does this mean? It's if there exists some positive real number n and a real number x naught, such that the absolute value of f of x is always bounded above by m times g of x for all x that's bigger than x naught. So what it's telling you is that this function f of x, for some value x naught, all x that's bigger than that x naught, f of x will be bounded above by g of x. That's all it means. It means that if you're sketching it on a plane, then if f is, a g will always be above f, so long as x is past the value x naught. Okay? And this is when x, of course, is going to infinity. But we can also use big O notation as x goes or approaches some particular value, let's say a. So we have the same setup where f of x and g of x. And then we say that f of x is equal to big O g of x as x tends to a if there's a positive real number m and a real number x naught, such that the absolute value of f is always bounded above by m times g of x for all values of x such that x minus a absolute value is in between 0 and x1. So usually this value a that we talk about is usually 0. So we usually want to understand what happens, and this is usually when we're talking about error terms, which we'll see quite a bit when we do quantum simulation. Okay, are there any questions so far? Okay. So let's look at an example of how we can use a big O notation. So when we analyze algorithms, when we're going to talk about efficiency, let's just talk about the time. So let's assume that the number of steps it takes to complete the running of this algorithm to solve some problem of size n. So the problem has some size n. So let's just say that the runtime is given by the function t of n, which is 4n squared minus 2n plus 2. As n grows large, so as the size of the problem gets larger, then the n squared term will dominate this expression, so that all the other terms can be neglected. So what we'll usually write is we'll say that the runtime for this algorithm, t of n, is equal to big O of n squared, meaning that it's always bounded above by some number times n squared. You're always bounded above that. So this is just how we use the big O notation to describe how an algorithm scales with the problem size. So the runtime of an algorithm, how does it scale with the problem size? So we'll be using this as well when we talk about constructing quantum circuits to do quantum simulation. Another place where we use big O notation, and we'll use it quite prominently in the school, is to describe the error term when we look at approximations of functions. So let's look at, for example, the exponential function. We can always write the exponential function in a Taylor expansion, which looks like this. And we can usually summarize this by saying that we'll chop off all the rest of the terms and go to infinity after the x squared term. And we summarize it by writing down big O x cubed. And all this means is that the error between, which is the difference between the exponential function and these three terms here, is at most some constant times the absolute value of x as x approaches 0. So all it allows us to do is it allows us to describe what is the limiting behavior, or what is the what function bounds the error term when you make this truncation of your series expansion. So this we're going to use quite a bit because we're doing approximations of the exponential function. So we'll see this a lot in quantum simulation. Okay, and the last mathematical preliminary that you'll need will be how to approximate functions of operators. So when we're doing quantum simulations, we usually want to construct some sort of function of this operator which will approximate our evolution or unitary evolution operator. So the way we describe how functions can be functions of operators will be can be approximated is we say if we have an operator A and an operator function f of A, we say that the function f tilde of A approximates f of A to a precision, which we call epsilon, which is bigger than 0 if the difference between these two operator functions, when you take the operator norm, is less than or equal to this precision epsilon. So that's how you always define these, like, how if we have some approximation, or we construct some sort of approximation to our operator function or the unitary evolution operator, we'll always check the difference between them and then take the operator norm, and then we will see, okay, if it's below our given precision, then we know we have an approximation of our unitary evolution operator. And yeah, something else we always talk about is when we talk about the order of the approximation. So the order of the approximation is the degree of the first non-zero term in the difference of the expansions. If you Taylor expand this and Taylor expand that, if it's an approximation, a bunch of the terms will cancel each other. So the first time that they don't cancel each other, whatever the degree of that term is, that's going to be what we call the order of the approximation. So if you go back, for example, here, we'll usually say that this series here approximates the exponential function up to order x cubed. So because the highest term is x squared and the error term will be x. Okay. Now I'll also just briefly formalize what we've already mentioned, which is just the quantum mechanics of closed quantum systems. So the reason why I spoke about Hilbert spaces is because a quantum system or a d-dimensional quantum system is going to be described by a Hilbert space. The state space of the quantum system is going to be described by the Hilbert space. And the state at some time t is described by a unit vector in the Hilbert space. So the state of the quantum system will be described by a unit vector in the Hilbert space. Unit vector means that the norm of this vector is always going to be 1. The dynamics of the system is always going to be described by the Schrodinger equation, okay, which we have here. And this Schrodinger equation, this H is a Hermitian operator, and Hermitian means that it's equal to its complex conjugate transpose. And this H is called the Hamiltonian. It's the total energy operator for the system, and H is what we usually use to describe what system we have. So usually you're given H and you need to solve the Schrodinger equation to figure out what the state at some time t will be. So the Schrodinger equation, you can always just solve it and write down a formal solution. And the formal solution is going to be our starting point for quantum simulation. Because the state at some time t is just u of t on psi 0, and this psi of 0 is just going to be the initial state. So the state of your system at some time t equals 0. And this u of t is just e to the minus I h t. That's all it's going to be. So where h is an operator, so you can see why now we needed functions of operators, because this unitary operator, which describes the evolution of our quantum state, is precisely a function of the Hamiltonian. It's precisely the exponential function. So this is the formal solution of the Schrodinger equation. And this u of t is a unitary operator, meaning it has the following, it satisfies the following condition. that when you multiply with its complex conjugate transpose, and vice versa, you have identity, which means its complex conjugate transpose is also its inverse. And what that means is that the complex conjugate transpose of u of t is just u at minus t. And this is very interesting that unitary transformations and the evolution of a closed system is what we call reversible, because you can always evolve your system backwards in time purely because of the symmetry that you have and the fact that this is a unitary operator. You'll see when we move to studying open quantum systems, we no longer have this reversibility because the evolution of an open quantum system is irreversible. We won't be able to just reverse it by saying u of minus t. To say that for open quantum systems does not make physical sense. But at least for closed quantum systems, we can do this. Okay? And usually this Hamiltonian H will be in the form of something like this, sum of many smaller terms, Hj, which are also, they have to be Hermitians for H to be Hermitian. And if one wants to describe the dynamics of the quantum system, then we have to be able to realize this u of t, which is the exponential of minus I over the sum of Hj on t. So we need to find the exponential of the Hamiltonian, which usually is a d by d matrix. And of course, if you've done any sort of programming, you know that finding exponentials of matrices gets harder and harder as the system size gets larger. So then we ask the question of why is it hard to simulate quantum dynamics on a classical computer? Because now that we know how this quantum system evolved, we can actually address why it's hard to do it on a classical computer. Well, we know that u of t can always be represented by some d by d matrix if your quantum system is d-dimensional. Okay? So let's consider a system of n spins. So spins are just two-level systems. The Hamiltonian describing a single spin is just a 2 by 2 matrix. Okay? So that's, if you need to take the exponential of a 2 by 2 matrix, it's fairly easy, right? But what if we have n spins? Then you have a 2 to the n by 2 to the n matrix. So what do we see when we look at this? If we want to take the exponential of this Hamiltonian, we need to exponentiate a 2 to the n by 2 to the n matrix. And if we need to use it as a unitary operator, it means we need to store a 2 to the n by 2 to the n matrix. So what does it mean? It means that as the number of spins grow, what happens? As the number of spins grows, then the size of your matrix is going to grow exponentially. So that's what we talk about when we say that a classical computer struggles with handling the exponential growth of the Hilbert space. Because if you want to study something like 300 spins, you need a 2 to the 300 by 2 to the 300 matrix. And I don't know exactly what the number is, but I know 2 to the power 300, 400, somewhere around there, something along the order of the number of atoms in the universe or something. But yeah, so this is the exponential growth that the classical computer struggles with. Okay, and when we talk about quantum simulation, we're going to see how easy it is that we don't need 2 to the n by 2 to the n matrix to do quantum simulation, the simulation on a quantum computer. We just need, an n-qubit unitary gate, which if you've done any quantum computing, that's fairly easy to realize. So I've given a mini school previously on quantum computing, so I'm not going to go into too much detail. But if you don't know what it is and you want to read about it, I'll give you just an idea. In quantum computing, we make use of quantum systems called qubits. These are just two-level systems. And we perform computations by applying a sequence of quantum gates, which are just unitary transformations or unitary operations, to the qubits. And when you perform measurements to obtain the output of your computation. That's effectively describing quantum computing in this way I can say it. And this is just a little picture of the whole process. So if you have sort of like n qubits in some initial state, you use quantum gates to perform the evolution and perform the computation, and you measure at the end to get the output of your computation. So this is the model of quantum computing that we use. It's digital quantum computing, and this is what we're going to be using to solve the problem of quantum simulation. Okay? So we're finally there after all of the, some will be boring mathematics, some maybe revision. we can now formally state the problem of quantum simulation that we will be solving for the next coming weeks. So, given an initial state, psi of 0, a simulation time, t, that's bigger than or equal to 0, and some precision epsilon, as well as this Hamiltonian in the following form, the quantum simulation problem is to construct an approximation u of t to the unitary operator that you see here, u of t, such that the operator norm of the difference is below a precision epsilon, less than or equal to precision epsilon, and such that the operator here, this approximation, can be implemented efficiently with a polynomial number of quantum gates on a quantum computer. So this overall is the very general way of stating quantum simulation problem. And it's the problem that we're going to be tackling for the next few weeks. So on the surface, it doesn't look too complicated. It looks a bit easy, but if you've done any mathematical methods course, you know that when you need to do the exponential of a sum of operators, it's quite tricky because you can't just split them up like you would the exponential of a sum of numbers. So exponential splitting is one of the methods that we will look at to solve this problem. And we actually come to see that using these methods, this exponential splitting, I think the research started around 1986. And all the way up until 2010, people were still working, and even to this day, people are still looking at how to split exponentials. It's a very complicated problem, whether they are looking for exact formulas, recursive product formulas, or even just linear combinations or product formulas. People are still trying to figure out what is the best way to approximate exponentials out of a sum of operators. It's a very interesting problem all in itself, and we use some of the results and even come up with results when we do quantum simulation because it's innately one of the problems that you need to solve. So that's going to be a challenge when you're trying to simulate this unitary operators. Even on a classical computer, doing this kind of thing is also hard. And we'll see when we talk about Trotter-Suzuki product formulas where the advantage of doing quantum simulation of this type of structure is. Even with such a simple method as Trotter-Suzuki product formulas, we'll already see an advantage over classical computers. And as we proceed, we'll talk about more novel methods that give us an even better advantage on classical computers and algorithms for simulating quantum dynamics. And I can finally just show you one more thing. We can go talk a bit more detail about this picture that I put up in the beginning. So now we know that the state at some time t is given by this u of t acting on psi of 0. And when we prepare psi of 0 on our quantum computer, we use the sequence of gates to realize the approximation u of t. And the output state of our quantum computer is going to be psi tilde of t. Okay? And we want a way to guarantee. So you may be asking the question of, in this picture, we talk about the distance between the output states and the output state of the true unitary evolution operator. But the quantum simulation problem is relying on finding the difference between the approximation of the unitary operator. The question might be, oh, if we bound this, then how does it help us in showing that the output state is an approximation of the true output state? Well, we have to go back to the inequality that I mentioned about the norm. In that, if we use, for example, just the Euclidean distance between psi of t and psi tilde of t, then using that norm, we can replace psi of t by this expression and psi tilde of t by that expression there. We can factor out psi of 0, and then we can just use that inequality that relates the operator norm of the difference of u of t and tilde of t to the Euclidean norm of this. And the Euclidean norm of this, because the quantum state is going to be 1. So we can just drop that, and we're just left with this, which is bounded above by epsilon. So we see that if we can find an approximation to the unitary operator u of t, such that it is approximated to a precision epsilon, then the output state of our quantum circuit will also be within some distance epsilon of the true quantum state psi of t. So that's why for the rest of this school, you won't find me talking about the distance between the approximated quantum state and the true state, because once we have this, then we know what the boundary is. So we're not interested in doing this unless you are trying to actually calculate some type of observable or something like that. But when we're developing the methods of simulating quantum dynamics, we're only interested in this norm of the difference between the unitary operator U of t and u tilde of t. That's all we're interested in. And lastly, there are many aspects to solving the quantum simulation problem. There's many places where people are actually doing work and are making strides in research because it's a very multifaceted problem. If you look at this problem, just the problem of preparing this initial state in a quantum computer is already a challenge. And there's an entire field devoted to this small subtask of a problem called quantum state preparation. You find people in the quantum machine learning community are constantly working on better ways to prepare this state. People are working on finding better and faster circuit decomposition for implementing quantum circuits on quantum computers, which is also just a sub-problem in quantum simulation, but is necessary because we want an efficient quantum circuit. You don't want a quantum circuit that will take an exponential that the time complexity is exponential in the system size. You don't want something like that because then it's going to take forever to run on a quantum computer. And people are also working on finding this approximation u tilde of t, finding better, more precise approximations that can be implemented efficiently on quantum computers. There's so many areas where people are working on developing methods for quantum simulation. And honestly, we won't even have enough time in the school to talk about all of them. So I will just talk about some of the major ones. But this is a very interesting field and it's growing every day. Everyone who works in this field, I think if you don't look at the archive for like a day or two, you already see 10 papers after 2 days and someone solving some problem and improving a bound and improving a precision. So it's a very fast and rapidly changing field. And I think it's worthwhile working in this field, whether as an application to your research or even working in this field as sort of your research of the fundamental research into this field. Yeah, and the last thing I want to talk about is this problem of when we look here and we have this output state psi tilde of t, even just the problem of reconstructing the state efficiently, performing the right state tomography is again a very complicated problem that people are working on daily. But what we want to talk about and what we are always interested in when we're tackling this problem is, can we come up with measurement procedures that will directly produce for us the measurement of the observable here without needing to reconstruct the state cycle? That's also something people look at when they try to solve the quantum simulation. And everything I've just mentioned, these are just small subcomponents of fields that we need to, and problems that we need to solve to be able to do quantum simulation efficiently and well on quantum devices. So even though I will talk about a lot of methods and existing results in the school, I just wanted this slide to let you know that there's so much that needs to still be done in this field. And if you're interested in doing research in this field, you're never going to be at a lack of problems to solve. There's always things that you can do to solve problems. So I think I'll just end it there for lecture 1. And then when we get to lecture 2, I will actually talk about the first method that we're going to use to solve the quantum simulation, which is going to be the Trotter-Suzuki product formula. So yes, thank you for your time. Okay, we'll take questions.
Yeah, thank you very much. And we have attendees in-house, and if they can have questions, they're welcome to ask them. Otherwise, yes, people online, please, you can raise your hand and you can give your right to talk and you're going to ask your question. No, I will make an announcement.
Are there any questions from anyone in the audience here? Okay.
Can I just make one comment? I think when we were doing the showing recognition, speech parts.
Ah, yes, I should have.
I mean, okay. Okay. I don't see that. Are there any questions online? So I think we can probably wrap it up for today, and I assume that we can make the slides available so that they will be available online, so that you can re-follow. And if some of the mathematical preliminaries will be challenging, I'm sure that if you see the slides, it's pretty much standard quantum mechanics with a little epsilon of twist, but not more than epsilon. Okay, I hope that you can see everyone next week, because next week we're starting to do something really interesting and probably unusual most. Okay, bye bye.